the computer, we have Ellie and Steven. We're joining you from MOSI. MOSI is the Museum of Science and Industry, and the science we brought for you today is all about the solar system. This week is all about the universe and exploring it, so we thought it would be good to give you an idea of what's out there and what we want to explore. Alright, if you have any questions, do make sure you put them in the chat, and either Ellie or Steven will be able to answer them for you. So what we have right here is I'm outside of MOSI. I am 300 feet from where we would have our sun. Now, do you guys know what the furthest planet out from the sun would be? It's not Pluto anymore, but it is Neptune. And if you were 300 feet out, the correct size of Neptune at that point would be about this big. So it's very, very tiny. And I'm just going to drop it here at 300 feet. And there it is, super, super tiny. If you can imagine that's a planet. We will walk on to our next planet. Do you know what the second closest planet would be? Well, we're going to find out a little further away. So while we walk, let me tell you a few things about Neptune, the planet you just saw. It's named after the god of the sea in ancient Roman mythology. And Neptune actually has some of the fastest winds in the solar system. The winds on Neptune are faster than the speed of sound, which is insane, right? So here we are, we're already at 210 feet, and we still haven't encountered another planet. Remember how small Neptune was as well. Alright, finally, we are to our next planet, another gas giant. This one is called, fittingly, Uranus. Now, Uranus is actually named for the Roman god of the sky and heavens, and it's a little bigger than Neptune. Whoops, almost dropped a planet. But not that much bigger. So we're going to put it down, Uranus there, okay? Tiny little planet, very, very far out from the sun. So distances in space are so vast, we actually don't often calculate them in terms of miles or kilometers. Sometimes we use astronomical units, which are kind of a made-up unit, called space. Sometimes we use light years, or even like hours, or like minutes, or like seconds. And that is the distance that light can travel in that amount of time. Very, very far away, we're getting closer to our next planet here. Do you know what the next one would be? I'll give you a hint. It's the planet with all the rings on it. And here we are, Saturn. Now Saturn is even a little bit bigger than the other two. There you see Saturn to scale of our model. And I'll put Saturn down here. Saturn is actually the least dense planet in our solar system. If you had an ocean big enough, Saturn would float on water. And another fun fact is the North Pole of Saturn is actually in the shape of a hexagon. It has a hexagonal storm brewing at its North Pole. So that's pretty interesting and a really cool thing to look up pictures of if you ever get a chance. Now we are finally at our largest gaseous planet here, the king of the gods in ancient Rome, Jupiter. Put Jupiter down there. Jupiter is the planet that has that big red dot on it. That is actually a storm that has been brewing on Jupiter for more than 400 years. Very, very fierce storm. And that is the last of our gaseous planets, our gas giants. We're going to start getting into our more rocky planets here. Almost to the sun we have Mars. Now Mars is so small, it's actually the size of a grain of salt on our model. A little bit of grain of salt there for Mars. It's a little bit smaller than the Earth, so I will also represent the Earth as a grain of salt. Now Mars and Earth are very close together. They have similar length days, and they both have water on their surface. Now, Earth is interesting in that it is the densest planet. It has the most mass per area, and it's also the only planet that has plate tectonics. So like earthquakes and things like that. Venus is next. Venus is very similar in size to Earth. So I will also get a grain of salt there for Venus. And Venus has an atmosphere that has a runaway greenhouse effect. Scientists think it might have been like Earth at one point, but because that atmosphere trapped in so much heat, it is now inhospitable for life. And finally, we have the tiniest planet. I'm not even going to put this thing of salt down there because Mercury would be the size of a speck of dust. It is the closest planet to the sun, very small, and also has almost no spin. So a year on Mercury is actually shorter than a day on Mercury. And here we would have the sun. In this model, the sun would be about the size of a ping pong ball. So now that you kind of have an idea of the sense of scale, let's move back inside where I want to show you a couple other activities that we have developed for you. Any questions so far? Again, feel free to put them in the chat if you do have any. We're going to ask some questions at the end so you can enter the drawing. It's the fun things, right? Okay. So, perfect, thank you. Okay. We're switching cameras, so if you are recording, you might want to highlight our webcam if you can see that. Let me know if you have any issues. The planets that you saw out there on kind of our solar system walk, they were to scale with the distance of the model we were doing. But it was kind of hard to get a sense of how big they were in comparison to each other. And that's why we have kind of a banana for scale here. Or in this case, fruit. So starting with the closest planet to the sun, the first one that you saw, we have Mercury. Mercury would be the size of a small pit or something very small, like that. Then the next planet we have would be, of course, Venus, about the size of a cherry tomato. And equal in size, we have the Earth. A little bit smaller than the Earth, we would have a blueberry. This is Mars. Yes. We're going to pause for just a second, make sure you guys can hear us.
They're saying they can't see you.
Also, I need that camera so you can get close-ups.
Okay, they can't, they're not going to be able to switch back and forth.
Okay, so let's keep just that one.
Okay. So, keep talking. They can still hear you.
Great. We're going to get a new camera up so you can see what's going on, guys, in just a second. Sorry about the technical difficulties. Ellie, do you have any questions yet? All right. Hopefully, if I can cut out, you might need to Okay, that looks much better. Okay. Let us know again if you have any issues. So to start again, we're talking about the size of the planets in comparison to each other. The size of the seed, the closest planet to the sun, would be Mercury, very, very tiny. And then next, Venus, size of a cherry tomato here. And finally, Earth, the same size. Kind of like sister planets in a way. And compared to the Earth, Mars is a little bit smaller. Mars would be a blueberry like this. Oh, and let me give you some labels. We have Mercury, we have Venus, we have Earth, and we have Mars. Now these first four planets, again, are rocky planets, very close to the sun comparatively, smaller, denser. And then we have our bigger gaseous giant planets. So, do you guys know what the biggest planet in the solar system is? Maybe you caught it while we were walking through. That's right, Jupiter. So we've got Jupiter here. This is represented by a watermelon, giant planet. Next one with the rings. It's a little small for Saturn, but Saturn would be the size of a large grapefruit there. And then Uranus, the size of an apple. And finally, the planet that we started off with, the furthest one from the sun, Neptune. Okay. So another thing I wanted to talk about with you guys is all the forces in the universe that are kind of keeping the planets in our solar system together. Now, there's these forces that act on planets, but they also act on us, they act on rockets, they act on penguins, they act on everything. And that main force that I'm talking about today is gravity. So if you look down here, we have what I like to call the fabric of space-time. And you'll notice that when you put an object on it, it does bend the fabric just a little bit, and it depends on how massive or dense that object is. So something like a marble is not going to bend my fabric as much as like a steel ball bearing would. And even that is only a little bit. So I've got a heavy steel ball here that's going to represent a star like our sun. And then these smaller ones would be more like our planets. So your Jupiter, your Uranuses, your Neptunes. And as those get close to a bigger, more massive object, you'll notice that they start to orbit around it. Now, our planets are eventually going to hit the sun here in our model, just because there is a little bit of friction on this fabric. But of course, in space, there's much less, there's no friction. So you're not going to have the same slowing. And if you have it just right, it'll spin around it for quite a long time. Now, this is a more massive one. This might work better. There we go. Nice. What I want you to notice as this is going around this planet, pay attention to the ball in the middle, the star here. You might notice a slight wobble, a slight wiggle happening there. And this is how astronomers actually look for other planets. They look for that little wiggle in the sun because as this ball is going around, it's exerting a little bit of force on this one. Remember Newton's third law. For every action, there's an equal and opposite reaction. So while the massive sun is pulling on the smaller planet is actually enacting a little bit of force on the sun too, much smaller, but enough to notice. And sometimes the planets can actually orbit each other if you get it just right. Or they can collide. If they're too close to each other, they actually condense. And that's how we believe some of the planets formed in the early solar system, is the forces of gravity were powerful enough and they were different in enough, or similar in size enough, that different clumps of dust and gases actually condensed together to form different bodies in our solar system, like moons and planets and all kinds of great things like that. This also is a good way to understand how black holes work. Do you guys know what a black hole is? It sucks in everything around it, right? What's that force sucking everything in? Well, just like everything else, it's gravity. A black hole is an area that is super, super dense. It has a lot of mass in a very little space. So I want you to imagine that this is a black hole, and it actually warps the fabric of space-time more than the objects around it. So even though it's small, these more massive objects are going to be able to get sucked in. Black holes are so dense, their gravity even sucks in light. Super, super powerful. Okay. And speaking of the early formation of the solar system, how are we doing on time? Awesome. I wanted to show you one other activity. Now you might have noticed that our solar system is a flat disk. Why is that? Can you think of any reason based on what we've talked about so far today why the solar system would be flat? Well, it has to do with angular momentum. So what I've got here for this experiment, this little demonstration, a black piece of paper, some different paint, and just a regular old salad spinner. And you can try this at home if you'd like. And we're going to start off our early universe, just like our solar system, 4.5 billion years ago. We've got a bunch of mass. And it's kind of all over the place. It's floating around in space. We've got different colors. And maybe it starts to condense at the middle because gravity pulls things together. They start falling towards each other, just like in our fabric. Let's add some pink. I like pink. Nice. Now remember, the center of our universe and the center of our solar system, the sun, is spinning. So as all of that mass kind of is condensing, but begins to spin, it all flattens out. And let's see what kind of nebula, what kind of early solar system we've got. Stop it there. Lovely. And you can see all of those things kind of flattened out and spread out from the center. Now, if you had chunks of more massive things in it, they would stay together, but they might fall further out. Just like those bigger gaseous planets. They had more mass, and they kind of went out further on the sides. Okay? And the smaller ones kind of got stuck in the middle. Okay. I didn't even see any yellow in there. Let me add some green. Add a little more mass, yellow like the sun. Nice, I like that one. I'll keep that off to the side. So I hope that gives you a little bit of a sense of why the solar system is flat. And it's actually, all of them are on the same plane that we call the ecliptic. So if you're out tonight and looking at the night sky, some of those stars that you see moving around are not stars at all, but actually planets. In particular, early in the evening, you might be able to see a particularly bright star. It's actually the planet Venus. And later on, you might see rising a more reddish one. Could be the planet Mars. And you can look for those the same way you look for the sun because they're all on the same plane. They rise in the east and they set in the west. And they move through our sky or appear to move through our sky. Remember, it's really the Earth that's spinning over the course of the evening. Okay, so now I have a few questions for you. My first question is, which of our 4 planets are gaseous and which of our 4 planets are rocky? Give you some time to answer that. Okay. And my second question is, yes, what force keeps all the planets in orbit around each other? It's the same force in black holes and stars. It's this kind of opposite force to entropy. Everything that's like spinning out of control in our galaxy, and then this force brings it all back together. Okay. So that's what I have for you guys. I know we have like 15, maybe 20 minutes left. No? Okay. Oh, okay. So that's all we got.
I was going to say, review the stuff outside.
I don't think we need to redo them again. Let me show you one other thing I do have though. Okay. So imagine Jupiter, just another kind of scale thing. Jupiter here is about a foot long. I wanted to show you how big the Earth would be in comparison to that. Or sorry, the sun. So if Jupiter is about a foot, our sun is this whole blue sphere here. So consider that's the biggest planet in our solar system, and then the sun is this massive object here. Okay. Now for comparison, you can look at our other planets. Okay. So you could have Saturn, even smaller. Even Jupiter, you could fit almost 1,000 Jupiters inside the sun. So imagine how many, for example, Neptunes you could fit in the sun. How many Earths could you fit in the sun? There's Earth. Okay. So I hope that this today gave you a better sense of the scale of things in our solar system. So if you are developing some sort of technology like the Voyager spacecraft, for example, that's going to go out and photograph all the planets, you need to consider how vast those distances are in space. And so, for example, the Voyager took more than 30 years to get from Earth to the very edge of our solar system. So anything you're designing needs to account for these vast spans of time as well as distance. And the technology that's going to be out there is going to be much older than the technology we have now, because it will have taken decades to get there. That's why every launch is so important, and every one needs to have a lot of forethought behind it. So you need to be thinking about projects decades in advance sometimes if you want to get information about even just the planets in our solar system. They are comparatively close. So if this was our solar system on the table here, the next star, the next solar system, Alpha Centauri, would be down the street, a few blocks that way. And remember, it took you 30 years to get here. How long do you think it's going to take you to get to our next star? That, again, is why we need to use these massive units like light years. So, for example, it would take light 8 years to get from here to the next sort of solar system that might have planets that we could land on. And that's if you're traveling with the speed of light, which we do not have in our technological capacity just yet. So thank you guys for learning a little bit more about our solar system today. I hope it was helpful. I hope you learned some cool facts about the planets maybe that you didn't know, and that you got a better sense of scale. Tomorrow what we're going to talk about is all about telescopes, and we're going to build a telescope, and we're going to talk about the different technology and devices that have allowed us to look at our universe and the world around us without having to actually travel there physically ourselves. Thank you so much for listening. This has been Catherine with MOSI, and we're happy to take any questions. Have a great day. Okay, I'm not sure how the questions are working. If there are any questions.
There's just statements. It's like Jupiter.
Jupiter? What about Jupiter? Oh, okay. Okay. Do you want to cut this and we can go to one of the computers?
Sure.
Oh, that was the answer to the questions. Perfect. Hi guys, back here in case there's any other questions. You're very welcome. Thank you for watching, and thank you for your patience with all the technical difficulties. Yes, those are the gaseous planets. Rocky planets. Nice, very good. And did anybody get the answer to what force is keeping all these planets in orbit and together in our solar system? Does anyone have a favorite planet, maybe? Okay.
I think we're good to go.
Yeah. Okay. Saturn is your favorite. Awesome. Thank you for answering. Okay, so if there are no other questions, we're going to sign off now. Again, thank you so much for listening, and we hope the rest of you have an amazing day. Keep discovering. We will see you tomorrow.